In this lesson, we'll discuss nitroenolates. Nitro compounds, similar to carbonyls, can be deprotonated, and they can undergo alkylation reactions and a reaction similar to the aldol. Let's look at alkylations first. Suppose we have a nitro compound with this structure. We can treat this with base, and the base is going to be able to deprotonate this acidic proton. And these electrons are going to have resonance stabilization with the nitro group. This forms an intermediate that looks like this. And now we can treat this with an alkyl halide. Now the electrons can push back down through the conjugated system, attacking here and displacing bromine. Now, nitro compounds might not be super useful in maybe natural product synthesis. Few natural products actually contain the nitro group, but plenty of them contain amines, and a quick reduction step will allow us to access these compounds. The nitro compounds can also be used to produce carbonyl compounds. Treatment with an oxidant in a base, for example these conditions here, allows us to access a ketone in this case because we have an R group over here. If R is H, these same conditions give us an aldehyde. Now let's look at the nitro analog of the aldol reaction. This reaction is called the nitroaldol or the Henry reaction. For this reaction, we'll start with nitromethane. I'm going to add in the proton that we want to deprotonate. And it's useful to mention here that we can use even mild amine bases to promote this reaction because the resonance of the resultant enolate with the nitro is so good. So we can use something like triethylamine to facilitate this deprotonation. And in this case, I'm going to skip showing all this resonance through the group and just put the anion on the carbon that's going to do the attacking. So just like with a carbonyl compound, we can show the deprotonation, facilitating the formation of a double bond in this resonance form, or we can show the deprotonation putting an anion on carbon. Now, we'll treat this with an aldehyde or a ketone. Here, I'm going to use an aldehyde because it'll allow me to show you a few subsequent reactions and what we can make from these compounds. We have this carb anion here. It can attack the electropositive carbon of the carbonyl, pushing the electrons up onto oxygen. This attack plus a protonation step gives us this nitroaldol product. Now we can react this product in a variety of ways to produce really interesting compounds. Like before, we can reduce this, and the nitroaldol product will afford us amino alcohols. Oxidation with chromic acid without a base present will oxidize just this alcohol right here. If we protect this alcohol here, we can then use these conditions to oxidize our nitro to the aldehyde. Deprotection of this compound will reveal an aldehyde and an alcohol in a 1-2 relationship. Now the nitroaldol produces an alcohol. With the aldol, we can promote dehydration pretty readily just by perhaps warming our reaction under equilibrating conditions. But in this case, we can still dehydrate. It just requires a second step. Here are some example conditions for dehydration, and this produces a nitroalkene. This nitroalkene can be converted to an aldehyde under these conditions. But the nitroalkene itself is also very useful in synthesis. This is an electron-poor dienophile, so it's a great partner for the Diels-Alder reaction. When heated with this relatively electron-rich diene, the Diels-Alder reaction can proceed, giving us a cyclohexene. The enolate of a nitro compound is distinct from the enolate of an aldehyde or a ketone. This is because the anion forms on the carbon that's attached to the group and not one carbon away. So when we're looking at products like this and perhaps thinking how we can use alkylation of a nitroenolate to do this, our disconnection is going to be adjacent to the functional group. And so if we want to think about this example retrosynthetically, our positive synthon comes from the right-hand side of this disconnection here, and our negative synthon is the equivalent of this. So this type of reaction actually represents a polarity reversal of an aldehyde or ketone. We usually expect the carbonyl carbon to be attacked, but the nitroenolate, is the synthetic equivalent of having an anion on that carbon, opening up new, unique reactivity.